Here's the question that haunts physicists and dreamers alike. What happens to time when you actually reach light speed? Does it stop completely? Today, we're diving into one of physics' most mind-bending mysteries, the relationship between velocity, time, and the fundamental structure of space-time itself. And here is a question for you. If you could travel at the speed of light, where's the first place you'd go? Let me know in the comments down below. I will pin the most creative answer. Also, make sure to subscribe and give a thumbs up. Now let's begin. The speed of light is the same for all observers, regardless of their motion. If you're standing still and measure a light beam, you'll find it travels at about 300 million meters per second. If you're on a spaceship racing at half the speed of light and measure that same beam, you'll still find it travels at 300 million meters per second. Not faster, not slower. This seems impossible. How can light always travel at the same speed regardless of the observer's motion? The answer rewrites everything we thought we knew about time and space. For light to always travel at the same speed, time and space themselves must be flexible, stretching and compressing depending on velocity and gravity. This isn't an illusion or measurement error, it's the fundamental fabric of reality. Time is not a universal constant. Space is not a rigid stage. Instead, they're interwoven into what physicists call spacetime, a four-dimensional fabric that bends, warps, and flows. Time dilation, the slowing of time at high velocities, emerges directly from this framework. As you accelerate toward light speed, time slows down for you relative to stationary observers. At 90% of light speed, every second that passes for you equals about 2.3 seconds for someone standing still. At 99% of light speed, the ratio becomes 7:1. At 99.9%, it's 22:1. The closer you get to light speed, the more extreme time dilation becomes, approaching infinity as you approach the ultimate velocity. This isn't theoretical speculation. We've measured time dilation countless times with atomic clocks, particle physics experiments, and even GPS satellites. The global positioning system orbiting above Earth experiences both special relativistic time dilation due to their velocity and general relativistic time dilation due to weaker gravity. Engineers must account for these effects, or GPS would accumulate errors of about 10 kilometers per day, rendering it useless. Every time you use your phone's navigation, you're experiencing proof that time is relative. Particle accelerators like the Large Hadron Collider at CERN routinely accelerate particles to 99.999991% of light speed, so close that these particles experience extreme time dilation. Muons created in the upper atmosphere by cosmic ray collisions should decay in about 2 microseconds, traveling only about 600 meters before disintegrating. Yet we detect them at Earth's surface because they're moving at near light speed, and time dilation extends their lifespan from our perspective. For the muon itself, experiencing time at its own rate, it lives only 2 microseconds, but space contracts in its reference frame, making the journey to Earth's surface much shorter. This brings us to length contraction, relativity's equally strange twin. As you approach light speed, not only does time slow down, but space itself compresses in your direction of motion. At 99.9% of light speed, distances shrink to about 4.5% of their stationary length. A journey to Proxima Centauri, 4.24 light-years away, would appear to contract to just weeks or months of distance from your perspective. The closer you get to light speed, the more the universe pancakes in front of you, squashing vast cosmic distances into manageable spans. But here's the catch that brings us back to our original question. Nothing with mass can actually reach light speed. Einstein's equations show that as objects accelerate, they gain relativistic mass, not physical mass you could weigh, but inertial mass that resists further acceleration. The energy required to accelerate an object increases as velocity increases, and at light speed, the energy requirement becomes infinite. To accelerate even a single electron to exactly light speed would require more energy than exists in the entire observable universe. This is why physicists say light speed is a limit, not a goal. Only massless particles, photons which carry light, and electromagnetic radiation, and possibly gravitons if they exist, travel at this cosmic speed limit. They don't accelerate to light speed, they're born traveling at light speed and can never slow down. From our perspective, photons zip across the cosmos at 300 million meters per second. But from a photon's perspective, something truly bizarre happens. If you want to explore the incredible barriers preventing anything with mass from reaching light speed, from the physics that make it impossible to the engineering challenges we'd face trying, check out my video Will Humans Ever Reach the Speed of Light?, where we examine exactly what would happen if we tried. The link is in the description and on the card above. Now let's explore what the universe looks like from light speed itself. From a photon's reference frame, time doesn't just slow down, it stops completely. The journey from its point of emission to absorption, whether across a room or across the observable universe, takes exactly 0 time from the photon's perspective. Imagine being a photon emitted from a star in the Andromeda galaxy, 2.5 million light-years away. From Earth's perspective, your journey takes 2.5 million years. But from your perspective as that photon, you're emitted and absorbed in the same instant. The beginning and end of your journey are simultaneous. You experience no passage of time whatsoever. This creates a paradox that reveals the limits of our ability to conceptualize extreme reference frames. We can't truly imagine what a photon experiences because experience requires time, a before, a during, and an after. At light speed, these distinctions collapse. Past, present, and future merge into a single, eternal now. Causality becomes meaningless when effect follows cause instantaneously. Length contraction becomes equally extreme. At light speed, all distances in the direction of travel contract to 0. From a photon's perspective, the entire universe along its path compresses to a single point. The vast expanses of space that take light years to cross from our perspective don't exist from the photon's viewpoint. It departs and arrives without traversing any distance because distance has contracted to nothing. This raises profound philosophical questions. Does a photon experience existence? Can we even speak meaningfully about the perspective of something for which time doesn't flow and space doesn't extend? Physicists generally say no. The concept of a photon's reference frame is mathematically undefined. Special relativity's equations contain a term that divides by the square root of 1 minus velocity squared divided by light speed squared. When velocity equals light speed, this denominator becomes 0 and you can't divide by 0. The math breaks down, telling us that asking about time from light speed's perspective is like asking what's north of the North Pole, a question that seems grammatical but lacks physical meaning. Yet we can approach arbitrarily close to light speed and examine what happens in the limit at 99.999999999% of light speed, let's call it 12 nines. Time slows by a factor of about 7,000. A journey across the galaxy that takes 100,000 years from Earth's perspective would take only about 14 years for the traveler. Push to 15 nines and the time dilation factor reaches about 22,000. The traveler could cross the galaxy in about 4.5 years of their time. As you add more nines, approaching ever closer to light speed without quite reaching it, time dilation approaches infinity. In principle, if you could reach speeds differing from light speed by infinitesimal amounts, you could experience arbitrarily short durations while external observers measure eons. You could, in theory, travel billions of light-years of distance while experiencing only years or even days of proper time. But you'd never quite reach light speed itself, never experience the infinite time dilation that would reduce your journey to zero duration. This asymptotic approach, getting closer and closer without ever arriving, characterizes much of relativity. Light speed acts as an asymptote, an unreachable limit that structures the entire framework. Massive objects can approach it arbitrarily closely but never reach it. Massless particles must travel at exactly light speed but can never slow down. The boundary between these regimes is infinitely thin, yet absolutely impassable. The universe enforces this limit through energy requirements. Accelerating to higher velocities requires increasingly enormous energy inputs. The Large Hadron Collider accelerates protons to energies of about 7 trillion electron volts each, achieving 99.99991% light speed. To reach even closer to light speed would require exponentially more energy. To reach 99.9999999%, adding just 2 more nines, would require roughly 100 times more energy per particle, far beyond current or foreseeable technology. Now let's examine what Einstein actually showed about time at different velocities. His equations predict that a moving clock runs slower than a stationary one, a prediction tested with extraordinary precision. In 1971, physicist Joseph Haffel and astronomer Richard Keating flew atomic clocks around the world on commercial airplanes. When they compared the flying clocks to identical clocks left at the US Naval Observatory, they found the predicted time difference, measured in nanoseconds, matching Einstein's predictions to within experimental uncertainty. Flying eastward, with Earth's rotation, the clocks lost about 59 nanoseconds. Flying westward, against Earth's rotation, they gained about 273 nanoseconds. These differences seem tiny, but they confirm that velocity affects time flow. Modern versions of this experiment use even more precise atomic clocks measuring time dilation at walking speeds. In 2010, physicists at the National Institute of Standards and Technology detected time dilation between 2 atomic clocks differing in elevation by just 33 centimeters, about the height of a single stair step. They also measured time dilation for relative velocities of less than 10 meters per second, roughly the speed of a jogging human. At these everyday scales, the effects are measured in parts per quadrillion, but they're real and measurable. The reason we don't notice time dilation in daily life is that the effects are proportional to velocity squared divided by light speed squared. For ordinary velocities, this ratio is vanishingly small. A car traveling at 100 kilometers per hour experiences time dilation of about 1 part in 100 trillion, utterly negligible. But as velocities approach light speed, the ratio approaches 1, and time dilation becomes dramatic. Visualizing this mathematically helps. The time dilation factor is 1 divided by the square root of 1 minus velocity squared divided by light speed squared. Let's call velocity v and light speed c. The formula is 1 over the square root of 1 minus v squared over c squared. At low velocities, where v is much less than c, this factor is essentially 1, no dilation. But as v approaches c, the denominator approaches 0, making the whole factor approach infinity. At exactly c, you divide by 0, which is mathematically undefined. This mathematical structure tells us something profound. Light speed isn't just a really high velocity we haven't reached yet. It's a fundamentally different regime, a boundary separating causally connected events from those that can never influence each other. In space-time diagrams, which plot space on one axis and time on the other, light travels along 45-degree lines called the light cone. Events inside your past light cone can affect you. Events inside your future light cone can be affected by you. Events outside both cones are absolutely disconnected from you. No signal, no influence can travel between you faster than light. This connects to causality itself. If you could travel faster than light, you could send signals into your own past, creating paradoxes. Imagine sending a message faster than light to a distant star, which immediately sends a message back faster than light. Due to the relativity of simultaneity, the fact that different reference frames disagree on what events are simultaneous, the return message could arrive before you sent the original message. You'd receive the reply before asking the question, violating causality and potentially creating grandfather paradoxes where effects precede causes. The universe seems structured to prevent such paradoxes. Light speed limit doesn't just constrain velocity, it protects causality, ensuring that cause precedes effect in all reference frames. This is why faster-than-light travel remains relegated to science fiction. It's not that we lack clever engineering, it's that FTL travel would require breaking the logical structure of space-time itself. But photons experience none of this causal structure because they experience no time. A photon emitted during the Big Bang traveled for 13.8 billion years from our perspective and absorbed by your eye right now experienced zero duration. From its perspective, the Big Bang and the present moment are the same instant. All of cosmic history collapses to a single eternal now for any massless particle. This timelessness extends to all massless particles. Gluons, which carry the strong nuclear force, binding quarks into protons and neutrons, travel at light speed and experience no time. Gravitons, if they exist as quantum particles of gravity, would also travel at light speed and experience no time. The fundamental forces, electromagnetism, strong force, possibly gravity, are mediated by particles for which time doesn't flow. This creates a strange dichotomy in physics. Matter particles, electrons, quarks, neutrinos, have mass and experience time. Force-carrying particles, photons, gluons, possibly gravitons, are massless and don't experience time. The universe's structure seems built on this distinction, with time-experiencing matter interacting via timeless force carriers. Neutrinos complicate this picture slightly. Long thought to be massless like photons, we now know neutrinos have tiny but non-zero masses. They travel extraordinarily close to light speed but not quite at it. The fact that neutrinos have mass, discovered through neutrino oscillation experiments in the late 1990s and early 2000s, means they experience time, albeit time flowing very slowly due to their extreme velocities. The evidence for neutrino mass came from observing neutrino flavor oscillation, neutrinos changing from one type to another as they travel. This oscillation requires the different neutrino types to have different masses, and quantum mechanics allows particles to oscillate only if they have mass. The measurement earned the 2015 Nobel Prize in Physics and revealed that our picture of massless versus massive particles was incomplete. This brings us back to the fundamental question, does time stop at light speed? The answer is nuanced. From the perspective of external observers, time for a light-speed particle appears to stop. Its clock, if it had one, would appear frozen. But from the particle's own perspective, the question becomes meaningless. Time doesn't stop for a photon because time never existed for it in the first place. Past, present, and future are human concepts requiring temporal flow. For massless particles, these distinctions don't exist. This leads to one of physics' most profound mysteries. Why does time exist at all? In our everyday experience, time flows inexorably forward. We remember the past, experience the present, and anticipate the future. Yet the fundamental equations of physics, from Newton's laws to Einstein's relativity to quantum mechanics, are mostly time-symmetric. They work equally well running forward or backward. If you filmed particles interacting and played the film in reverse, you'd see processes that obey physical laws just as well as the forward version. The arrow of time, the fact that time flows in one direction, emerges not from fundamental laws but from thermodynamics, specifically the second law, which states that entropy, disorder, increases over time in closed systems. This statistical tendency toward greater disorder gives time its direction. You can scramble an egg but not unscramble it because the scrambled state has higher entropy. The universe began in a low entropy state at the Big Bang and has been increasing in entropy ever since, creating the arrow of time we experience. But for photons, this arrow doesn't exist. They're outside the flow that gives time meaning for massive particles. In a sense, they witness the entire history of the universe simultaneously. The Big Bang, the formation of galaxies, the birth and death of stars, all experienced as a single, eternal instant. This timelessness has practical implications for understanding the universe. The cosmic microwave background radiation, the afterglow of the Big Bang detected by satellites like COBE, WMAP and Planck, consists of photons released about 380,000 years after the Big Bang, when the universe became transparent to light. These photons have been traveling for 13.8 billion years from our perspective, redshifted by cosmic expansion from visible light to microwave frequencies. Yet from each photon's perspective, no time has passed. They were emitted and absorbed instantaneously. When you tune an old analog television to a channel with no station, about 1% of the static you see comes from this cosmic microwave background, photons that began their journey before Earth existed, before our sun formed, before our galaxy assembled. Yet those photons experienced no duration. Their journey through cosmic history took zero time from their frame of reference. This perspective shift from our time-bound viewpoint to the timeless perspective of light offers a window into how profoundly relative time really is. There's no absolute universal now that extends across the cosmos. Simultaneity itself is relative. Events that appear simultaneous in one reference frame occur at different times in another frame, moving at a different velocity. Einstein demonstrated this with a thought experiment involving a train. Imagine lightning strikes both ends of a moving train simultaneously as measured by someone standing on the platform midway between the strikes. The person on the platform sees the light from both strikes arrive simultaneously, confirming they happened at the same time. But someone on the train, moving toward one strike and away from the other, sees the light from the front strike arrive before the light from the rear strike. From their perspective, the strikes weren't simultaneous. The front strike happened first. Neither perspective is more correct. Simultaneity genuinely depends on reference frame. There's no absolute answer to whether distant events happen at the same time, because at the same time has no frame-independent meaning. This relativity of simultaneity flows directly from the constancy of light speed. If light speed is the same for all observers, and observers are moving relative to each other, they must disagree about simultaneity to maintain consistency. This means the universe has no universal present moment. The now you experience extends only to your immediate vicinity. Distant events can be ordered as past, future, or ambiguous, depending on whether light could have traveled between them. This structure, called the light cone, divides space-time into regions you can causally influence, your future light cone, regions that can causally influence you, your past light cone, and regions space-like separated from you, with which you can have no causal interaction. At light speed, this structure collapses. A photon's light cone degenerates to a line. Everything in its path lies simultaneously in its past and future because it experiences no duration between emission and absorption. The photon connects disparate space-time points across billions of light-years and billions of years, yet from its perspective, these points are identical, separated by neither space nor time. This is why physicists say photons don't have a valid reference frame. Special relativity's mathematics break down when you try to transform to the photon's perspective. The Lorentz transformations, the equations that translate between different reference frames, become undefined at light speed. You can take the limit as velocity approaches light speed, finding that time dilation approaches infinity and length contraction approaches total collapse, but you can't evaluate the transformation at exactly light speed. Some physicists explore what happens in this limit using advanced mathematics. They find that the photon's world line, its path through spacetime, has zero proper time and zero proper length. It connects 2 points in spacetime with a null interval, meaning the spacetime distance between them is zero. In a sense, the photon's emission and absorption occur at the same spacetime point, despite being separated by vast spatial and temporal distances from our perspective. This might seem contradictory, but it reflects spacetime's geometry. In special relativity, the spacetime interval between two events is calculated as the time difference squared minus the space difference squared, using appropriate units where light speed equals 1. For events connected by light, this interval equals 0. They're separated in space and time in just the right proportion that the spacetime distance vanishes. General relativity, Einstein's theory of gravity, adds more complexity. In special relativity, we deal with flat spacetime, no gravity, no acceleration. In general relativity, mass and energy curve spacetime, creating what we experience as gravity. This curvature affects how time flows. Clocks in stronger gravitational fields run slower than those in weaker fields, an effect called gravitational time dilation. This is separate from velocity-based time dilation but follows similar principles. Near a massive object like Earth, space-time curves such that time flows more slowly. GPS satellites, orbiting about 20,000 kilometers above Earth's surface, experience weaker gravity than clocks on the ground. This makes their clocks run faster by about 45 microseconds per day compared to ground clocks. Combined with velocity-based time dilation, making them run slower by about 7 microseconds per day, the net effect is about 38 microseconds per day faster. Near extreme gravitational sources like black holes, time dilation becomes dramatic. At a black hole's event horizon, the boundary beyond which nothing can escape, time appears to stop from the perspective of distant observers. An object falling toward the event horizon would appear to slow down, asymptotically approaching the horizon but never quite crossing it from the outside view. Yet from the falling object's perspective, it crosses the horizon in finite proper time and continues toward the singularity. This creates apparent paradoxes similar to those at light speed. From outside, an object at the event horizon experiences infinite time dilation and appears frozen forever. From the object's perspective, time flows normally and it crosses the horizon quickly. Both perspectives are valid in their reference frames, but they describe dramatically different experiences of the same event. Black holes thus create regions where time effectively stops relative to distant observers, similar to how time stops for photons relative to massive observers. The similarity isn't coincidental. At the event horizon, the escape velocity equals light speed. To escape, you'd need to travel at light speed, which is impossible for massive objects. The event horizon is effectively a surface of infinite time dilation, separating the interior, causally disconnected from the exterior universe. Photons at a black hole's event horizon can orbit in an unstable photon sphere, endlessly circling the black hole at light speed. These photons experience no time, but they're trapped in a circular path by spacetime curvature. They're null geodesics, the paths light follows through curved spacetime, loop back on themselves. From their timeless perspective, they're simultaneously everywhere on their orbit, emitted and absorbed at the same instant, despite tracing a circle around the black hole. Inside the event horizon, space-time curvature becomes so extreme that all paths lead inevitably toward the singularity. Time and space swap roles in a sense. Moving forward in time necessarily means moving toward the singularity, just as being alive on Earth necessarily means moving forward in time. Escape isn't merely difficult, it's impossible in the same way that traveling backward in time is impossible. The singularity lies in your future, not a place in space, but a moment in time you cannot avoid. Near the singularity, quantum effects become important, and our classical understanding of spacetime breaks down. We lack a complete theory of quantum gravity to describe what happens there. String theory, loop quantum gravity, and other approaches attempt to reconcile quantum mechanics with general relativity, but none are proven or complete. The singularity might not be a point of infinite density, but rather a region where space and time as we know them cease to exist, replaced by quantum foam or other exotic structures. These extreme scenarios, black hole singularities, the Big Bang, the end of time in a collapsing universe, represent places where our physics reaches its limits. They're cosmic laboratories where time itself might begin, end, or behave in ways we can't yet describe. Understanding time at light speed touches on these fundamental limits, revealing how time isn't a background stage, but an active participant in cosmic drama. Let's return to practical measurements of time dilation. Particle physicists routinely observe time dilation in accelerators. Particles called pions, created when high-energy protons collide, have a rest lifetime of about 26 nanoseconds before decaying. Yet pions traveling at 99.5% of light speed live about 10 times longer from our perspective due to time dilation. This extended lifetime allows them to travel meters or tens of meters before decaying, far beyond the few meters they could travel at rest. Similarly, cosmic ray muons created in the upper atmosphere, traveling at near light speed, live long enough to reach Earth's surface despite their 2-microsecond rest lifetime. Without time dilation, they decay in the upper atmosphere, and we detect far fewer at ground level. The fact that we measure copious muons at sea level confirms that their clocks run slower due to their extreme velocity. These aren't theoretical predictions, but observed facts. Time dilation is as real as gravity or electromagnetism, confirmed by thousands of experiments over more than a century. Every particle accelerator, every GPS satellite, every high-precision atomic clock experiment reinforces the reality that time's flow depends on velocity and gravity. This leads to practical applications. Future space travel, if we ever achieve significant fractions of light speed, would involve time dilation. A journey to Alpha Centauri, 4.4 light-years away, at 90% of light speed would take about 4.9 years from Earth's perspective, but only about 2 years for the travelers. At 99% of light speed, the journey would take 4.4 years from Earth, but only 8 months for travelers. The closer to light speed, the more dramatic the difference. This creates the famous twin paradox. Imagine twins where one stays on Earth while the other travels to a distant star at near light speed and returns. When they reunite, the traveling twin has aged less than the Earth-bound twin. This seems paradoxical because special relativity says all motion is relative. From the traveling twin's perspective, Earth moved away and returned. Shouldn't the Earth-bound twin have aged less? The resolution involves acceleration. Special relativity applies to inertial, non-accelerating reference frames. The traveling twin must accelerate to turn around at the distant star, breaking the symmetry. During this acceleration, the traveling twin switches reference frames, and the resolution involves understanding how different reference frames define simultaneity. The bottom line, the traveling twin genuinely ages less, a prediction confirmed by experiments with atomic clocks on airplanes and satellites. This means that if humans ever achieve near light speed travel, Astronauts could journey to distant stars and return within their lifetimes while centuries or millennia pass on Earth. They'd be time travelers of a sort, moving into Earth's future without experiencing the intermediate years. The stars themselves wouldn't seem as far away due to length contraction. Distances would compress from the traveler's perspective. But we can never quite reach light speed, never experience the infinite time dilation and total length contraction that photons experience. The universe enforces this boundary strictly. As you accelerate, not only does further acceleration require more energy, but your mass effectively increases from the perspective of external observers. At 99.999% of light speed, your relativistic mass is about 224 times your rest mass. The energy you've gained manifests as inertia resisting further acceleration. To reach exactly light speed would require infinite energy, which is impossible. Only particles born massless, photons, gluons, can travel at this ultimate speed. They don't accelerate to light speed, they're created traveling at light speed and can never slow down. A photon in vacuum always moves at exactly light speed, neither faster nor slower, from the moment of creation until absorption. This invariant speed of light is the foundation of relativity. Einstein didn't derive this from deeper principles, he elevated it to a postulate based on experimental evidence. The Michelson-Morley experiment in 1887 attempted to measure Earth's motion through the supposed luminiferous ether. The medium light was thought to travel through. They found no variation in light speed regardless of Earth's motion, suggesting light speed is constant in all directions. This null result puzzled physicists until Einstein realized it revealed something profound. Light doesn't need a medium. It travels through vacuum at a constant speed in all reference frames. This seemingly simple idea has staggering consequences, forcing us to abandon absolute time and absolute space in favor of relative space-time. Modern tests of light speed constancy use lasers, atomic clocks, and satellites, measuring light speed to extraordinary precision. The speed of light in vacuum is now defined as exactly 299,792,458 meters per second. We use this to define the meter itself. The distance light travels in 299,792,458th of a second. Light speed isn't measured anymore. It's a defined constant used to establish other measurements. This definitional status reflects our confidence that light speed is truly constant. No experiment has ever detected variation in vacuum light speed with direction, observer motion, or time. While light slows in materials like glass or water due to interactions with atoms in vacuum, empty space, it always travels at c, the cosmic speed limit. Quantum mechanics adds another layer to understanding light and time. Photons are quantum particles exhibiting both wave and particle properties. The Heisenberg uncertainty principle limits how precisely we can simultaneously know certain pairs of properties like position and momentum. For photons, this creates interesting constraints on how we can describe their behavior. A photon's wave nature means it's not precisely localized, it's spread out over its wavelength. When we say a photon travels from point A to point B instantaneously in its reference frame, we're dealing with a classical description that quantum mechanics complicates. Quantum field theory, which combines quantum mechanics with relativity, describes photons as excitations of the electromagnetic field. These excitations propagate at light speed, carrying energy and momentum. In quantum field theory, the photon's timeless perspective becomes even harder to interpret. Fields exist at all points in space-time, and particles are transient disturbances in these fields. A photon is a quantum of electromagnetic field, created and destroyed but not experiencing existence in the way massive particles do. The field is fundamental. The photon is an excitation that propagates at light speed. This framework explains how light mediates electromagnetic force. When charged particles interact electromagnetically, they exchange virtual photons, quantum fluctuations, that pop into existence briefly before being absorbed. These virtual photons can have properties ordinary photons can't, like non-zero mass, because they exist only momentarily within quantum uncertainty limits. But real photons, those we can observe, are always massless and travel at light speed. The quantum vacuum itself is filled with virtual particle pairs constantly appearing and disappearing. Photons pair produce with antiphotons, which are identical to photons, electrons with positrons, quarks with antiquarks. These quantum fluctuations exist for durations so brief they don't violate energy conservation within uncertainty limits. They contribute to measurable effects like the Casimir force and the Lamb shift, confirming that even empty space seethes with quantum activity. In this quantum picture, asking whether time stops for a photon becomes even more peculiar. Photons aren't persistent objects with continuous existence. They're created and destroyed, flashing in and out of reality. Between emission and absorption, the photon exists as a propagating wave in the electromagnetic field. What experiences time? Not the photon, which has no rest frame, but perhaps the field itself, which exists at all times. Quantum mechanics also reveals that particles can be in superposition, simultaneously in multiple states until measured. A photon can be in a superposition of different paths, traveling multiple routes simultaneously until detected. The famous double-slit experiment shows this. Send photons one at a time through two slits, and they create an interference pattern as if each photon passed through both slits simultaneously, interfering with itself. From the photon's timeless perspective, all these paths exist simultaneously, not because the photon experiences them in sequence, but because time doesn't differentiate beginning, middle, and end for the photon. The entire probability distribution of where it might be detected exists as a timeless whole. Only measurement collapses this distribution to a specific outcome. This connects to the measurement problem in quantum mechanics, the question of how and when quantum superpositions collapse to definite states. Various interpretations offer different answers. The Copenhagen interpretation says measurement causes collapse. The many worlds interpretation says all outcomes occur in branching universes. The de Broglie-Bohm interpretation posits hidden variables guiding particles along definite paths. For photons traveling at light speed, these interpretations must grapple with the timelessness of the photon's journey. In many worlds, does the branching occur from the photon's perspective or only from time-experiencing observers? In Copenhagen, does the photon's wave function exist in a superposition throughout its journey? Or does its timeless nature mean emission and absorption are a single event with no intermediate state? These questions touch on deep foundations of quantum mechanics and relativity. Reconciling these theories remains one of physics' grand challenges. Quantum mechanics brilliantly describes the microscopic world. General relativity beautifully describes gravity and space-time curvature, but they use incompatible mathematical frameworks. Quantum field theory successfully combines quantum mechanics with special relativity, but struggles to incorporate gravity. String theory, loop quantum gravity, and other approaches attempt to unify quantum mechanics with general relativity into a theory of quantum gravity. These theories might reveal that space-time itself is quantized at the Planck scale, about 10 to the negative 35 meters, where quantum effects dominate gravity. At these scales, time might not be continuous but discrete, existing in indivisible quanta. If time is quantized, what does that mean for photons? Do they experience not smooth timelessness but a frozen sequence of time quanta? each infinitesimally brief? Or does quantization apply only to massive particles experiencing time? These questions remain speculative, awaiting experimental tests of quantum gravity that might never be possible with current technology. The Planck time, about 10 to the negative 44 seconds, represents the shortest meaningful duration in quantum gravity theories. Below this timescale, quantum fluctuations make the very concept of time ill-defined. For photons experiencing zero duration, are they somehow interacting with reality at scales where time itself becomes fuzzy and uncertain? Recent experiments probe time's quantum nature. Physicists have created time crystals, states of matter that repeat in time rather than space, breaking temporal symmetry. They've demonstrated quantum entanglement across time, linking measurements at different moments. They've shown that quantum superposition can involve temporal states, with particles existing in superpositions of different times. These exotic phenomena reveal that time at quantum scales behaves strangely. Combined with relativity showing that time at high velocities and strong gravity behaves strangely, we're left with a picture of time as far more mysterious than the simple ticking of a universal clock. Time is flexible, relative, possibly quantized, and intimately connected to space-time geometry, quantum states, and entropy. For photons exempt from time's flow, none of these complications exist. They simply connect two space-time points with zero interval, mediating electromagnetic interactions, carrying energy across the cosmos, enabling us to see the universe. Every observation in astronomy relies on photons traveling from distant sources to our telescopes. We see the universe's past, not its present, because light takes time to reach us from sources light-years or billions of light-years away. The most distant objects we've observed, galaxies detected by the James Webb Space Telescope from when the universe was only a few 100 million years old, emitted their light over 13 billion years ago. Those photons traveled through expanding space, redshifted by cosmic expansion, finally detected by our instruments after a journey spanning most of cosmic history. Yet from each photon's perspective, the journey was instantaneous. Emission and absorption occurred simultaneously in the photon's timeless reference frame. This creates a profound connection between the ancient universe and the present moment. The photons reaching us from the cosmic microwave background, from distant quasars, from newborn galaxies near the edge of the observable universe, all experience zero duration. In a sense, the early universe and the present moment are connected by these timeless messengers, bridging eons from our perspective, but no time from theirs. This timeless perspective offers a strange kind of immortality to light. Individual photons might be absorbed and new ones emitted, but the electromagnetic field pervades all of space-time, connecting moments across cosmic history. The light from the Big Bang still fills the universe as the cosmic microwave background. The light from the first stars still travels through space, stretched by expansion, but still propagating. The universe is filled with light from every epoch, each photon experiencing no duration, all of cosmic history present simultaneously from light's perspective. This leads to a beautiful symmetry. We are made of atoms forged in ancient stars, assembled from material billions of years old. Yet we observe the universe through light that, from its perspective, experiences no age at all. We are ancient matter, observing through timeless light, both products of cosmic evolution, both essential to the universe understanding itself. The fact that light doesn't experience time might seem like an abstract curiosity, but it has practical implications for understanding the universe's structure. Photon geodesics, the paths light follows through curved spacetime, are null curves, paths of zero spacetime interval. These geodesics define the causal structure of spacetime, determining which events can influence which other events. In cosmology, we use photon geodesics to trace the history of cosmic expansion. The redshift of light from distant galaxies tells us how much the universe expanded during the light's journey. The cosmic microwave background's temperature and fluctuation patterns reveal conditions when the universe became transparent, just 380,000 years after the Big Bang. All of cosmology relies on analyzing light from distant sources, light that experienced no time but traveled through billions of years of cosmic expansion from our perspective. This observer dependence of duration extends beyond photons. Any two observers in relative motion will disagree about durations and distances. There's no absolute answer to how long a journey takes or how far apart objects are. It depends on who's measuring. This relativity is fundamental, not a measurement limitation or illusion. Time and space genuinely differ for different observers. The philosophical implications are profound. If time isn't absolute, if its flow depends on velocity and gravity, what is time really? Is it a fundamental aspect of reality or an emergent phenomenon arising from deeper physics? Some physicists argue that time doesn't exist at the universe's most fundamental level, that it emerges from quantum entanglement, thermodynamics, or other processes. The Wheeler-DeWitt equation, which attempts to describe quantum mechanics of the entire universe, contains no time variable. In this framework, the universe doesn't evolve in time. It simply exists as a wave function encompassing all possible states simultaneously. Time emerges from correlations between different parts of this wave function, not as a fundamental backdrop, but as an internal measure of change. If this view is correct, Photon's timeless perspective might be closer to fundamental reality than our time-experiencing perspective. We perceive time flowing because we're complex systems with memory embedded in an environment increasing in entropy. But at the deepest level, perhaps the universe is timeless, and our experience of time is a limited perspective on a more fundamental, timeless reality. This connects to the block universe concept where past, present, and future all exist equally. From this view, the universe is a four-dimensional space-time block, and the flow of time is an illusion arising from our consciousness, moving through it, or, alternatively, from our memories, creating a sense of past distinct from present. Photons experiencing all of their world lines simultaneously exemplify this timeless perspective. Contrasting views maintain that time is fundamental and flows objectively. The growing block universe theory says the past and present exist, but the future doesn't yet. Presentism says only the present exists, with past and future being merely concepts. These competing philosophies reflect deep uncertainties about time's nature. Relativity doesn't resolve these philosophical debates but constrains them. Whatever time is, it must be relative, dependent on reference frame, flexible enough to dilate and contract. It must be intimately connected to space in a unified spacetime. It must be affected by mass and energy through spacetime curvature. Any theory of time must accommodate these empirical facts. The experimental precision with which we've tested relativity is extraordinary. Time dilation has been measured to parts per trillion using atomic clocks. Gravitational time dilation has been confirmed from centimeters of height difference to light years of distance to massive objects. GPS relies on accounting for both effects every microsecond. Particle accelerators routinely observe time dilation for particles at near light speed. The theory is tested millions of times daily in practical applications. Yet we still don't fully understand time's relationship to quantum mechanics. The measurement problem, the arrow of time, the emergence of classical behavior from quantum superposition, all involve deep questions about time's role in quantum mechanics. The fact that photons don't experience time makes them ideal probes of these questions. How do timeless particles mediate time-dependent processes? how does measurement collapse occur from a timeless photon's perspective? Recent quantum experiments have explored time's quantum properties. Physicists have demonstrated quantum entanglement between particles at different times, showing that quantum correlations can span temporal as well as spatial separations. They've created quantum superpositions involving temporal states where a particle is in a superposition of existing at different times. These experiments suggest that time at quantum scales is as strange as space at those scales. The intersection of quantum mechanics, relativity, and our understanding of time points toward a deeper theory we haven't yet formulated. Quantum gravity, when we finally develop it, will likely reveal new insights about time's nature. Some physicists speculate that time emerges from quantum entanglement, that the correlations between entangled particles create the temporal structure we experience. Others suggest time is fundamental but quantized, existing in discrete units at the Planck scale. String theory offers intriguing possibilities. In some string theory frameworks, spacetime itself is emergent from more fundamental structures, vibrating strings or branes in higher dimensional spaces. Time might not be a dimension in the deepest theory, but rather an effective description that emerges at scales larger than the string length. Photons, as excitations of the electromagnetic field, would be emergent objects in this picture, their timeless perspective reflecting the timeless nature of the underlying reality. Loop quantum gravity takes a different approach, quantizing space-time geometry itself. In this framework, space consists of discrete quantum loops and time advances in discrete steps. The smooth, continuous space-time of general relativity emerges from averaging over these quantum structures, just as smooth water emerges from countless molecules. For photons, traversing this quantum space-time might involve jumping from loop to loop at light speed, experiencing no duration, but following a discrete path through quantized space. These speculative theories remain unproven, but they illustrate how deeply the question, does time stop at light speed, connects to fundamental physics. Answering it fully requires understanding quantum gravity, the nature of space-time, the origin of time's arrow, and how consciousness and memory create our experience of time's flow. Meanwhile, the practical answer remains clear. From an external observer's perspective, time for a photon appears to stop. Infinite time dilation makes the photon's clock, if it had one, appear frozen. From the photon's own perspective, the question is meaningless. Photons don't have reference frames in special relativity. The equations break down, telling us we're asking a question without physical meaning. Yet this mathematical breakdown itself reveals something profound. The universe has boundaries of description where our theories reach their limits. Light speed is such a boundary, separating massive particles from massless ones, time-experiencing observers from timeless messengers. Understanding these boundaries helps us appreciate both the power and limitations of our physical theories. Einstein's genius was recognizing that light speed's constancy required overthrowing absolute time and space. A century later, we're still exploring the implications. Every GPS satellite, every particle accelerator, every astronomical observation confirms his insights. Time is relative, space is relative, and together they form a unified space-time that curves, flexes, and shapes the cosmos. The fact that we can understand these concepts, that human minds evolved on Earth can grasp the nature of light, time, and relativity, is itself remarkable. We're made of atoms forged in stellar furnaces, arranged by evolution to contemplate the universe's deepest mysteries. Our brains, complex structures of neurons firing electrical signals at chemical synapses, somehow generate consciousness capable of understanding that time stops at light speed, that the universe is woven from space-time, that we're participants in cosmic evolution. This human connection to the cosmos, our ability to understand it, our origin in stardust, our brief existence in the vast sweep of cosmic time, makes questions about time and light more than abstract physics. They're questions about our place in reality, our relationship to the universe, the nature of existence itself. When we ask whether time stops at light speed, we're asking about the fundamental structure of the reality we inhabit. And the answer, as often in science, is both simpler and stranger than we initially imagined. Time doesn't exactly stop at light speed. It becomes undefined, inapplicable, a concept that loses meaning in a regime where duration collapses to zero and distance contracts to nothing. Photons don't experience time stopping. They simply don't experience time at all. This timeless existence, impossible for us to truly imagine, pervades the universe. Every ray of sunlight, every radio wave, every X-ray from a distant pulsar exists in this timeless state. Light fills the cosmos, connecting every moment to every other moment through messengers that experience no duration. The universe communicates with itself through light, and from light's perspective, all of cosmic history is one eternal now. As you look at the stars tonight, remember that the light entering your eye left those stars years, decades, or centuries ago. It traveled through the void, experiencing no time, connecting that distant moment to your present observation. You're seeing the universe's past through messengers that don't experience the journey between then and now. In a very real sense, you're in direct contact with ancient light, bridging time through timeless photons. This connection extends across cosmic scales. The light from the Andromeda galaxy, 2.5 million light-years away, shows us that galaxy as it was 2.5 million years ago when our ancestors were just beginning to use stone tools. Yet the photons carrying that image experience no duration. They connect that ancient moment to your eyes now, collapsing 2.5 million years to zero from their perspective. The cosmic microwave background surrounds us with light from 380,000 years after the Big Bang. These photons have traveled for over 13 billion years, redshifted by cosmic expansion from visible light to microwave frequencies. Yet they experience no time. The baby universe and the current cosmos are connected by these timeless messengers, simultaneous from the photon's perspective, despite being separated by almost the entire history of the universe from ours. This creates a beautiful paradox at the heart of cosmology. We observe the universe's history by collecting ancient light, photons that left distant sources billions of years ago. We reconstruct cosmic evolution from these observations, tracing how galaxies formed, stars ignited, and structure emerged from the nearly uniform early universe. Yet the photons carrying this information experience none of that history. For them, emission and absorption are the same instant, separated by neither time nor space in their reference frame. We, as time-experiencing observers, witness cosmic history through timeless messengers. The universe's story unfolds across billions of years from our perspective, yet the light showing us this story experiences no duration. Past and present, distant and near, all connected by photons for which these distinctions don't exist. This relationship between observer and observed, between time-bound consciousness and timeless light, exemplifies the deep strangeness of relativity. Reality isn't a single, absolute structure, but a web of perspectives, each equally valid, each seeing different durations, distances, and simultaneity. The photon's perspective is as valid as ours, even though we can't fully describe it mathematically. The question, does time stop at light speed, ultimately reveals more about our relationship with time than about light itself. Time is something we experience, measure, and use to organize our understanding of causality. Light, traveling at the cosmic speed limit, exists outside this temporal framework. It doesn't experience time stopping. It exists in a regime where time never applied in the first place. This distinction matters for understanding the universe. As we develop better theories, quantum gravity, theories of everything, we'll likely find that our time-bound perspective is limited, that the universe's deeper structure is more like the photon's timeless reality than our duration-filled experience. Time might be emergent, not fundamental, arising from quantum correlations, entropy increase, or other mechanisms. Yet for us, living our brief lives on Earth, time flows relentlessly forward. We age, stars burn, galaxies evolve, the universe expands. The arrow of time points inexorably from past to future, and we ride this arrow from birth to death, experiencing the passage of moments even though relativity tells us time is relative and possibly emergent. This tension between our experience and physics' deeper insights creates the wonder that drives science. We're embedded in time, yet we can understand timelessness. We move through space, yet we can grasp spacetime. We're made of matter, yet we can comprehend how massless particles behave. Consciousness emerging from atoms, asking questions about the cosmos, discovering that reality is stranger than imagination. This is the human story. As we conclude this journey into time, light, and relativity, remember that you're part of this cosmic story. The atoms in your body were forged in stars, assembled on Earth, organized by evolution into a being capable of pondering time's nature. You exist for a brief moment in cosmic history, experiencing time's flow while the universe around you operates on principles that transcend time. The photons striking your eyes right now, carrying information about the world, experienced no journey from source to eye. Whether from the sun, 8 light minutes away, or from your computer screen, millimeters away, each photon experienced 0 duration. The universe's light connects moments across space and time, yet experiences neither space nor time. When you look up at the night sky, you see light from different epochs. Some stars light from years ago, others from centuries past, the Andromeda galaxy from 2.5 million years ago. Yet all these photons arrived at your eye, experiencing no time, connecting past to present in an instant from their perspective. You're observing history through timeless messengers, witnessing the universe's story through particles for which that story has no duration. This is the magic of physics, revealing that reality operates on principles we can understand but can barely imagine experiencing. Time stops at light speed not because clocks freeze but because time itself becomes meaningless for massless particles. They exist outside time's flow, connecting space-time points with null intervals, mediating forces, carrying energy, showing us the cosmos. Thank you for joining me on this exploration of one of physics' most profound questions. I hope you now appreciate how deeply time, light, and relativity intertwine, how our time-bound experience is just one perspective in a universe of valid reference frames, and how Photon's timeless existence reveals fundamental truths about space-time structure. Keep looking up at the stars, keep asking impossible questions, and remember, you're made of ancient stardust experiencing the universe through timeless light. Your existence spans mere decades, yet you're connected to billions of years of cosmic evolution, observing through photons that experienced no time, thinking with atoms that experienced all of it. You're the universe contemplating itself, time-bound consciousness, pondering timeless light. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I am sure you will love this other video at the left side of the screen. What if we could travel at light speed today? Discover what would actually happen if you could accelerate to the speed of light, from time dilation and length contraction to the Doppler effect, relativistic aberration, and much more. See you there.